Here, and today we are going to be looking at the probability distribution of binomial outcomes. We covered this yesterday in class. We had this example where we looked at binomial probabilities, and what we saw was when we have a bunch of things that we have to do in a row, like if we want to find the probability of no more than the first six, then we have the probability of none, and or the probability of one, or the probability of two, or all the way to 6. And what we saw was, let me just do TI, that we can put this into our calculator as a binomial function in the binomial CDF, and we can take care of this quite quickly. So for this example specifically, we have 20 trials and the like. So we have, for example, I would just go down here to my distribution, go down to the binomial distribution, number of trials, 20, probability, it was a dice, 1/6, and then I wanted the first 6, right? From 0 to 6, I wanted to stop at 6, no more than 6, so 6 will result. So that means not 7, not 8, not 9, not all the way to 20, not those, so I want 6. So we get about 96%. Okay, let's look at letter E. So E, probably none rule of 5. Well, that's probability x is 0. And for this, it would just be 20 choose 0 times 1/6 to the 0 power times 5/6 to the 20th power. Well, this is 1, so that goes away. This is also 1, so this is just 5/6 to the 20th power. So we need to do between 8 and 12. Now, I don't know how I would do this on the calculator. I'm not going to lie. I would probably just be forced to do this by hand, unfortunately. So this would be 20 choose 8, 1/6 to the 8, 5/6 to the not 8, 12, plus 20 choose 9, 1/6 to the 9, 5/6 to whatever's left over. And I would just have to do this through. We don't usually see a lot of problems like this just because of the hassle that this puts us through, but we can solve this. It would just be brutal and time consuming and really not worth the effort. Just overall. So, but we can do those. We just don't see them very often. And if they do, it wouldn't be 8, 9, 10, 11, 12. It wouldn't be 5 options. It'd probably be 2 or 3. So if you would want, like, let's say, like exactly between 8 and 10, we would do 8, 9, and 10. Those are doable. 5 gets a little bit ridiculous. So the binomial model, just in general, binomial model. So that's what we were looking at. Binomial. These are counting successes here. And what do these look like? Well, binomial model, the average is the expected value, which is the number of things that we have times the probability of it happening. I mean, if you think about how this would work out, it will make sense. You never have to prove this. I think there's a proof in the textbook somewhere, but this is just what's true about this model. So we also have the standard deviation. So that's sigma here. Standard deviation of x is the square root of the number of things that you have times the probability of them happening times the probability of them not happening. So just for good measure, that means that the variance is simply n the number of things times the probability of the thing of success times the probability of failure. And again here, let's just say P is success, Q is failure. But that's what it is, because P is like whatever we're looking for, the probability of that happening. Q is whatever's left over. When we take 1 minus P, we get Q. So for this to be true, though, for us to be able to use this nice model, because this is a model, we want it to be, all the things that we want to happen with a model to be true. And for that to happen, we have a condition, at least one condition, We need more than 10 successes and more than 10 failures. So probability of success, so I'm just going to write more than 10 successes and more than 10 failures. And what does this look like? Well, because these things up here, these are the probability. This is an expected value, but P is a probability of success. Q is the probability of failure. So these values will always be between 0 and 1. These will be decimals. Well, we want the number of successes. So how do we find these? Well, we just simply will take the number of things happening. It's essentially the expected value. We want the expected value to be greater than or equal to 10. And the expected failures, N times Q, to be greater than or equal to 10. There is a proof actually in your book for this. I don't think you need to know the proof, but it's actually a pretty elegant proof. So if you want to look, this is on page 424. I'm not going to bore you with the proof, but I do think that it's worth looking at if you're really enjoying this section. Am I right, guys? Am I right? Okay, so let's look at it. We have an example here. It says international students at a certain college, 6% of all students come from outside the United States. Incoming students there are assigned at random to freshman dorms where they live in residential clusters of 40 freshmen sharing a common lounge area. How many international students would you expect to find in a typical cluster? What is the standard deviation? Okay, so these are Bernoulli trials, right? If we think about this, there are only two possible outcomes. You either are international, so we have you are international or not, right? You're one or the other. So the probability of a freshman is international, we're told is 6%, so probability, so let's let P equal probability of international, whatever that says. So P is 0.06. And we want, let's see, incoming student freshmen are, we have to consider, like, are these independent, right? Because we want to use some sort of a model here. We want to really look at these Bernoulli trials, this idea of a binomial distribution. These have to be independent, so they might not be, honestly. So one thing we have to assume, like if these might not be independent, so let's assume that the population of freshmen is greater than 10% of the sample. Right, because our sample size here is 40, so we're looking at the 10% condition. So we want our population to be less than or equal to 10%. So I'm assuming that the freshman population at this place, at this school that we're looking at, I don't even know. All students, yeah, this is definitely true. If this is a countrywide statistic, there's obviously more than 400 freshmen. So this is definitely assumable. That definitely met here. Got that. So, this works for us because even if they're not independent, there's definitely more than 400 freshmen. So what expected value of this would just be 40 times 0.06, right? So this is approximately 2.4 students. Standard deviation, this would just be the square root of 40 times 0.06 times 0.94, which is approximately 1.5. And that's it. And that's it. Yeah, what's the standard deviation? How many would we expect? Well, we expect 2.4 students. What's the standard deviation? 1.5 students. Nothing to it, just like geometric distribution. Once you just know the formulas, you just kind of plug them in there and you are ready to go. I don't want to note. Chapter 3. Red cross. Let's see. Okay. This one. Did I miss one? No. Suppose the Red Cross anticipates the need for 180 units of O-negative blood. It estimates that will collect from 32,000 donors. How great is the risk that they will fall short? And this says, why will the binomial not help us? International. So I believe for this one, so I know what the population is. So population, I'm not told. Suppose so P is 0.06, Q is 0.94. So the need for at least, hold on, I have this. This is in the book. Hold up. Do I have, so this one times 50 and Q. Least. That estimates population from a blood donor. How great is the risk? I don't see anything here that would tell me that this is a normal distribution. I don't know. Let me come back to it. I'm skipping it. We'll come back to it if we have to. Consider LeBron James in the cereal boxes. So this is like the one that we looked at before. Remember that he is only found in 20% of cereal boxes. We're buying 5. So these are the probabilities when we buy 5 cereal boxes. And you'll notice here, you'll notice here that this is not a normal distribution. Quite skewed. So we're buying 5 boxes. So this is what the distribution would look like when we buy 5 boxes. And for us, that's an issue because we want things to be normal. So why is this not normal? Why is this not normal? Let's look. We want LeBron. Let's say like we want LeBron, right? So probability, P being the getting a LeBron card is 0.2. Okay, and we're doing 5 boxes. So one thing that we just said is that we need the probability of success to be greater than 10. Well, what's 0.2 of 10? Is that, or what's 0.2 of 5? Is that greater than 10? No, that's not true. How many boxes would we need? Let's consider buying 50. Okay, all right, okay. What's 1/5 of 50? You guessed it. Consider buying 50 cereal boxes and count the number of LeBron pitchers we will find. This histogram shows the distribution with a center of 10, which we would expect, right? Because our expected value is the number that we have times the probability of it happening, 10. Boom. Mean, middle. And notice that 50 times 0.2 is greater than or equal to 10. We got our success. And also, the 50 times the failure would just be the rest of them. So both of these meet this model. And notice now how having this amount of cards, or boxes rather, gives us what we need, also yielding something that is approximately normal. This is a big deal for us because we want things that are approximately normal. When we have them, we can use all of our things that we know. Z-scores, probability of things happening, etc. This is really, really big for us, and it's very, very helpful for us to do statistical inference. Look at this, Pew Research Center. Do I have this one or am I using a different one? I'm using a different one. Big blood. Yeah. We're doing this one. 0.76. Is this one? No, is it this one? 0.7. Oh, yeah, we're doing this one. Okay, I'll read it. So let's think about the Pew Research Center pollsters one more time. They tell us that they are successful at contacting 76% of households randomly selected from telephone surveys. That's a lot. When surveying public opinion, they hope to poll at least 1,000 adults. Suppose Pew has compiled a list of 1,300 phone numbers to call. What's the probability that they'll reach enough people? Let's look at A, okay? So we got this going on. Let me just put this here. So despite the fact that the pollsters sample without replacement, can we think of these as being independent? Pause the video and see what you think. So for A, let's see. Are they independent? No, probably not, right? Even if they're random, probably not. But is 1,300 houses greater than 10% of all adults? Yeah. Yes. So even if they're not independent, it doesn't matter. We can think of them as independent because the 10% condition is met. B, find the mean standard deviation. X equals Pew. Okay, so the mean would just be the expected value, which is simply 1,300 times 0.76. And that's the mean mu. And then we have our standard deviation of X, which would be the square root of 1,300 times, 0.76 times the whatever's left, 0.42. Close that up. And this is 15.4. And again, that would be sigma there. So easy peasy, squeeze the lemon. And then C, we want to find the probability that X is greater than 1,000. Can we use the normal model to approximate this? Yes, we can, because we see that N times P has to be greater than 10, and N times Q, the failures, have to be greater than or equal to 10. These are way bigger. I mean, this is 988. And this would just be the rest of them. I guess I'm not going to do that. I'm going to do this. The rest of them, 12. So easily beats that condition. And now find the approximate probability that they will contact at least 1,000 voters. So we need to do X minus mu over sigma. Let's get a standard deviation here. So X is 1,000, 1,300. Standard deviation for us. Oh no, mu was, do I have a value for this? Did I miss this somewhere? 988. My bad. I do have it. So let's see what our Z score is here. So this is 0.779. So how about 0.78? So as I'm doing my normal curve, this is 0, 1. So this will probably be somewhere around here. And I want X is greater than 1,000. So I want everything to the right. Where's that calculator at? So I'm going to do my distribution, normal CDF. Normal CDF. And we're going from 0.78 to infinity. 0, 1, because it's normal. And we have approximately 22.7%. So normal CDF. So I want my upper bound, or my lower bound, which is 0.78. I want my upper bound, which is infinity, 0, 1, equals 0.227. And to finish this off, to the probability of reaching at least 1,000 voters on the list is about 22.7%. So, yeah, that's what we got. Let's look at one more. The blood drive. All right, back to the blood. Let's see. I have this one. I know that. So, before a blood drive, Red Cross agency puts out a plea. Please, come universal blood donors and give us your blood, hoping that they'll get more than 6%, more than the usual 6% to show up. That day, they collected 202 units. That's a lot of blood, and among 17 were O negative. So that's our donors there. Does this suggest that making a public plea was an effective way to get more O negative donors to come to the blood drive? So let's see. What do we want to do? Well, let's just state the problem. Let's just say is 17 O neg donors of 2002 people statistically significant. That's what that says. Statistically significant. Is this statistically significant evidence? How do you spell that word? Evidence that the plea was effective. Is that what is it? Was the fee? All right, so let's see. We got 17 out of 202. Okay, so let's see what we can do. Okay, so first thing I'm going to do is I'm going to let X be the number of O neg blood donors. Okay, so let's see. Are these independent trials? Probably not. Probably not. However, can we meet the 10% condition? Can we meet so is 202 greater than 10% of all possible donors? Yeah, for sure. For sure. Definitely that there are. So let's even if we have to, we can assume at least 2020 blood donors, which I think that's reasonable to assume. I think that this condition is very easily met and is assumable easily. What about successes and failures? Are there enough? Well, we have to say n times p is greater than 10, and n times q is greater than 10. So 202 times 0.06 is greater than 10, and 202 times 0.94 greater than 10. Is it greater than 10? Yep, it is. It is. Both of these work. 202 times 0.06, 12. And then this is just going to be 1 minus, or my bad, not 1. It's just the complement. Whatever that is. I'm not doing that in my head. I guess I'll do it in my head. This is 1, 9, 1, 8. I'm not doing it. All right, I'll do it. 1, 8, 9, 8, 8. Let me know if I'm wrong. I'm pretty sure that's right. But that does. This meets our thing. So so we have successes. We have this. So we're looking really good so far. In our possible conditions. So this tells us the successes. This tells us, approximately normal here. We're good with that. Its sample size is sufficiently large, which again is reinforcing our approximately normal conditions, because that's what we want to use. So let's just see. We have our expected value, which is n times p, which I did above, which is 1212. Standard deviation, which is just the square root of npq, which is 3, 3, 0.75 like that. And so I can find a z-score, right? I want to know, is 17 statistically significant? Did this have a big impact on the outcome? Okay, so what could we do? Well, how about we use the normal CDF? Let's see. Here's 0, 1, 2. So this would probably be somewhere in here, 1.45. So let's use a normal CDF. And see what's the probability of maybe less happen. You could use the 90 whatever rule here too, the empirical rule. But let's just see both sides of this, see what we come out with. So I'm just going to do negative infinity to 145, 0, 1. Negative infinity, 145. So the probability of being over here in red, here, let me do a highlighter. Is 0.926, and we'll leave it there. And then this is just the rest of this, which would be 0.8, 0.74, 074. Is this statistically significant? Did this have a big impact? Well, I don't think so. Because if you recall, things that we say are unusual happen usually within about 95% or more or less. Like, so to be statistically significant or unusual, we would want it to be, we would want this part of this to be less than or equal to 5%. And it's close, but it's not quite there. So is this statistically significant? It's better than 92%, 93%-ish of turnouts, but it's not there. If it were better than 95% of turnouts, I would say, okay, now this is statistically significant. So even though 17 was a really good turnout, that's going to be a no for me, dog. And that's actually where we end this lesson and where we end this unit, is considering, can we use binomial things to actually give statistical evidence to say, yes, this is significant turnout, or no, it's not, and why? And like we examined before, that threshold that we're really looking for is 95%. Thanks for watching.